Hi, welcome to lecture 8A. This video will cover the steady state and transient response of RC circuits. In this video, we will discuss the definition of steady state response of RC circuits, examples of steady state response of RC circuits, then definition and examples of transient response of RC circuits, and finally, natural response and step response of RC circuits. Now, at the beginning, let's discuss about the steady state condition. When a circuit remains in a condition for a long time, that condition is considered as a steady state condition. For example, if a circuit remains in a condition such that the switch is off for a long time, we say that the circuit is in a steady state condition. Similarly, if a circuit remains in a condition for a long time such that the switch is on for a long time, we say that the circuit is in a steady state condition. There could be two states of a circuit to remain in steady state condition. Those are initial condition and final condition. It is important to remember for a circuit with a capacitor that under steady state DC condition, capacitor is equivalent to an open circuit. Hence, a capacitor can be replaced by an open circuit as shown in the figure if the circuit is supplied by a constant DC voltage source. In this instant, we may review slide 10 of lecture 7a, and that says that the capacitor current is proportional to the rate of change of voltage. That means I equals C dV dt. Therefore, when a constant DC voltage is applied to a capacitor, dV dt becomes zero, and hence the current across the capacitor will be zero. Let's take an example of a steady state condition. Determine the steady state values of I1, I2, and Vc for the following circuit when the switch is closed for a long time. If the switch is closed for a long time, the circuit is in steady state condition. Hence, the capacitor C can be replaced by an open circuit. And then the circuit will contain a voltage source and three resistances. Here, 10 ohm resistance will be in parallel with 15 ohm, which will make equivalent 6 ohm resistance, which will be in series with 4 ohm. That will give the total resistance of the circuit as 10 ohm. Then the current through the 4 ohm resistance will be total voltage in the network 30 volt divided by the total resistance in the network 10 ohm, which will give 3 ampere current. Then the voltage across the resistance Vc will be 3 ampere multiplied by the 6 ohm resistance, which will give 18 volt. Then the current through the I1 branch, that will be 18 volt divided by the 10 ohm resistance, which is 1.8 ampere, and the current through the I2 branch will be 18 volt divided by 15 ohm, which is 1.2 ampere. Now we would like to discuss about the transient condition. When we suddenly switch on a voltage source in a circuit, the voltage will build up across the capacitor. During this build-up time, the voltage varies with time. This time-varying voltage is known as transient response. For example, if a circuit remains in a condition such that suddenly the switch is turned on from the off position, we say that the circuit is in a transient condition. In this circuit, the capacitor will start charging after the switch becomes on. Similarly, if a circuit remains in a condition such that suddenly the switch is turned on from the off position, we say that the circuit is in a transient condition. In the right-hand circuit, the capacitor will start discharging after the switch becomes on. Here, note that the voltage source is being disconnected from the capacitor. As we have seen, There could be two types of response from a circuit during the transient condition. Those conditions are known as natural response and step response. We will be explaining those in a minute. Transient response of RC circuit will be divided into two phases. First one is the natural response. Natural response is in such a condition when stored energy in a capacitor is suddenly released to a resistive network. Only consider the nature of the circuit itself, not external source of excitation. Then step response is a phenomena when energy is being acquired by a capacitor due to sudden application of a voltage source. In this case, sudden application of an external source of excitation is considered. So it doesn't happen naturally. Now we will explain the natural response of an RC circuit. During the natural response, a capacitor will be discharging. Suppose an ideal capacitor is charged to a voltage of V and then is disconnected from the DC source. Further, at time t equals 0, the capacitor is switched on to a resistor as shown in the figure. Applying KVL to the circuit with switch closed, we get minus Vt plus Rit equals 0. We know that the current through the capacitor I equals C dV dt. Substituting the value of the current, we will get RC dV dt plus Vt equal 0. Now the equation can be written as dV dt plus 1 over RC Vt equals 0. By integrating the above equation and considering voltage V0 at time t0 and voltage Vt at time t, we will get Vt equal V0 e to the power minus t over Rc. Here Rc, the product of the resistance and capacitance, is known as the time constant for the RC circuit, which is denoted as tau. Here tau equal RC. Hence the final equation of the discharge of a capacitor is Vt equal V naught e to the power minus t over tau. Now we will take an example of the discharge of a capacitor. The capacitor discharging characteristics will be drawn below with initial voltage V0, 10 volt and time constant tau equal 5 second. The table shows the value of Vt with respect to t. When t is 0, Vt is calculated as 10 volt. When t is 5, Vt is calculated as 3.6. When t is 10, Vt is 1.3. When t is 15, Vt is 0.4. When t is 20, Vt is 0.1. When t is 25, Vt is 0.06. We can see that with the increase of t, Vt is decreasing. Now on the right hand side, we have drawn the voltage with respect to time, and it shows that at t equals 0, Vt was 10, at t equal 5, Vt was 3.6, at t equal 10, Vt was 1.3, t15, Vt 0.4, t20, Vt 0.1, t25, Vt around 0, which is 0.06. So this graph is showing the natural response of a capacitor or the discharging characteristics of a capacitor, and the equation for this capacitor discharging characteristics in this case is 10 e to the power minus t over 5. Now we will explain the step response of an RC circuit. During the step response, a capacitor will be charging. Suppose a capacitor is connected in series with a resistor and being charged by a voltage source. When the switch is closed in the circuit, as shown in the figure, we will get the equation RIT plus VT equal VS. VS is the voltage source in this case, and which is connected to the resistance and capacitor. By substituting the value of current IC equals C dV dt in this equation, we will get dV dt plus 1 over tau Vt equal Vs over tau, where time constant tau equal Rc. By solving the differential equation above, we will get Vt equal Vs 1 minus e to the power minus t over tau. Now we will take an example of the charging of a capacitor, which will be a step response. In this case, the capacitor charging characteristics is drawn below, same as the capacitor discharging characteristics, with source voltage V0 as 10 volt and time constant tau equal 5 seconds. In the table, we see that when t is 0, Vt has been calculated as 0. T is 5, Vt is 6.4. T is 10, Vt is 8.7. T is 15, Vt is 9.6. T is 20, Vt is 9.9. T is 25, Vt is 10. What we have drawn here on the x-axis T time and on the y-axis V voltage. When t is 0, Vt was 0, and then t is increasing from 0 to 25, Vt is increasing from 0 to 10, and all of the points have been drawn here. So here we see in the graph the capacitor charging characteristics. So with respect to time, capacitor charge is increasing, capacitor voltage is increasing, capacitor is being charged, and the equation for capacitor charging characteristics is Vt equal Vs, which is the source voltage, multiplied by 1 minus e to the power minus t over tau. Now we will discuss a general solution for step and natural response. The first order differential equation with a constant excitation is of the form of dx dt plus 1 over tau xt equal k, where k is a constant. The general solution to the above differential equation is given by xt equal x infinity plus x0 minus x infinity e to the power minus t over tau. Here xt is a variable dependent on time. In circuit analysis, this x can be either voltage function Vt or current function It. And x0 value is the value of the variable x at time 0, or the initial value, and x infinity is the value of the variable x at infinite time, or final value. So this x equation can be either a voltage equation or a current equation to describe the step response and natural response of a capacitor or of an inductor. Now we will summarize the solution steps for transient and steady state response of RC circuits. The first step, draw the circuit for t less than or equal 0, either with switch open or closed according to the circuit condition. Then determine V0. Step 2, draw the circuit for t greater than or equal 0 with switch closed or open depending on the circuit, and in this case determine the V infinity, and then calculate the time constant tau for t greater than or equal 0, and in this case you calculate the tau, which is R multiplied by the C of the circuit. Then calculate the capacitor voltage by using the following equation: Vt equal V infinity plus V0 minus V infinity e to the power minus T over tau, where tau equal R multiplied by C. The same procedure could be applied for capacitor current equation as well. Now let's take an example of the transient and steady state response of an RC circuit. The switch is in position A for a long time prior to t equals 0. Then at t equals 0, the switch is moved to position B. Derive an expression for the capacitor voltage VCT. Now to solve this circuit, we will follow the steps as mentioned before. That step 1 was draw the circuit for t less than or equal 0 with switch is in position A, and then calculate V0, which is 10 divided by 15 plus 10 multiplied by 100 volt, which gives us 40 volt. And then step 2, draw the circuit for t greater than or equal 0 with switch is in position B. And in this case, calculate the Vc infinity, which is 0. Then calculate the time constant tau for t greater than or equal 0. Time constant tau equal R multiplied by C for the final circuit, where R is 100 kilo ohm and C is 20 microfarad. This gives us 2 seconds. And finally, step 4, calculate the capacitor voltage by using the equation Vt equal V infinity plus V0 minus V infinity e to the power minus t over tau. So in this case, VCT we equal V infinity, which is 0, plus V0, which is 40, minus V infinity, which is 0, e to the power minus t over tau, where tau is 2. And finally, we get the capacitor voltage, that is 40 e to the power minus t over 2. Now let's summarize all the important equations that we have learned so far. For natural response or discharging a capacitor, Vt equal V0 e to the power minus t over tau. Step response, charging a capacitor, Vt equal Vs1 minus e to the power minus t over tau. For transient and steady state response of RC circuits, Vt equal V infinity plus V0 minus V infinity e to the power minus t over tau. And then finally, time constant of the RC circuits to be calculated at t greater than or equal 0, that is tau equal R multiplied by C. Now you know all of the equations. Let's try to solve the example questions. Hi, welcome to lecture 8B. This video will cover the steady state and transient response of RL circuits. In this video, we will discuss about the definition and examples of steady state and transient response of RL circuits and natural response and steps response of RL circuits. So at the beginning, let's discuss about the steady state condition. When a circuit remains in a condition for a long time, that condition is considered as a steady state condition. For example, if a circuit remains in a condition such that the switch is off for a long time, we say that the circuit is in a steady state condition. Similarly, if a circuit remains in a condition for a while such that the switch is on for a long time, we say that the circuit is in steady state condition. There could be two states of a circuit to remain in steady state condition. Those two conditions are initial condition and final condition. It is important to remember for a circuit with an inductor that under steady state condition, inductor is equivalent to a short circuit. Hence, an inductor can be replaced by a short circuit as shown in the figure if the circuit is supplied by a constant DC current source. We have seen in lecture 7b, slide 10, that the inductor voltage is proportional to the rate of change of current, which says V equal L di dt. Therefore, when a constant DC current is driven through an inductor, di dt equals 0, and hence the voltage across the inductor becomes 0. Let's take an example of a steady state condition. Determine the steady state values of I1 and I2 for the following circuit when the switch is closed for a long time. If the switch is closed for a long time, the circuit is in steady state condition. Hence, the inductor L can be replaced by a short circuit. Here, 10 ohm resistance is in parallel with 15 ohm resistance, which makes the equivalent resistance of 6 ohm. And then this equivalent 6 ohm resistance is in series with 4 ohm. That gives the total resistance of the circuit is 10 ohm. Now the current through the 4 ohm resistance will be total voltage 30 volt divided by the total resistance 10 ohm, which is 3 ampere. And then the voltage across the 6 ohm parallel equivalent resistance would be 3 ampere multiplied by 6 ohm, which will be 18 volt. Finally, the current through the branch I1 will be the voltage across that branch, that is 18 volt divided by 10 ohm, which gives 1.8 ampere, and then current through the branch I2 will be 18 volt divided by 15 ohm, which gives 1.2 ampere. Now we will discuss about the transient condition of an RL circuit. When we suddenly switch on a current source in a circuit, the current will flow through the inductor. During this build-up time, the current varies with time. This time varying current is known as transient response. For example, if a circuit remains in a condition such that suddenly the switch is turned on from the off position, we say that the circuit is in transient condition. In this circuit, the inductor will start charging after the switch becomes on. Similarly, if a circuit remains in a condition such that suddenly the switch is turned on from the off position, we say that the circuit is in a transient condition. In this circuit, the inductor will start discharging. Similar to the capacitor, here we would like to mention a general solution for step and natural responses of an RL circuit. The first order differential equation with a constant excitation is of the form of dx by dt plus 1 over tau xt equal k. The general solution to the above differential equation is given by xt equal x infinity plus x0 minus x infinity e to the power minus t over tau. Here xt is a variable dependent on time. In circuit analysis, it can be either voltage function Vt or current function It. And x0 is the value of the variable x at time 0 or initial value, and x infinity is the value of the variable x at infinite time or at final value. Hence, the steps that we follow for transient and steady state response of RL circuits are as follows. Step 1, draw the circuit for t less than or equal 0 with switch open or closed depending on the circuit condition. Then determine I0 for this condition. Step 2, draw the circuit for t higher than or equal 0 with switch closed or open depending on the circuit condition. And for that condition, determine I infinity. Step 3, calculate the time constant tau for t greater than or equal 0, and at that time determine tau, which is for an RL circuit tau equal L over R. Step 4, calculate the inductor current by using the following equation, which is IT equal I infinity plus I0 minus I infinity e to the power minus t over tau, where for RL circuit tau equal L over R. Now we take an example of the steady state and transient response of RL circuits. Assuming that Vs source voltage equal 10 volt, resistance R equal 1 ohm, and inductance L equal 5 Henry, and the inductor carries no current at the start, which means initial current I0 equals 0. Derive an expression for the inductor current ILT for the following circuit. Now to solve this problem, we would follow step-by-step procedure. Step 1, draw the circuit for t less than 0 with switch is opened. The circuit is shown here, in which case we see an open circuit. So in that case, there will be no current. So IL0 is 0 ampere. Step 2, draw the circuit for t greater than or equal 0 with switch closed. And for this circuit, our current IL will be Vs over R, total voltage divided by the resistance according to Ohm's law. And here total voltage is 10 volt and total resistance in the circuit is 1 ohm, which gives us a current 10 ampere. Step 3, calculate the time constant tau for t greater than or equal 0. For RL circuit, tau equal L over R. L in this case 5 Henry and R is 1 ohm, which gives the tau as 5 second. Step 4, calculate inductor current by using the equation IT equal I infinity plus I0 minus I infinity e to the power minus t over tau. Here ILT equal I infinity, which is 10 ampere, plus I0, which is 0, minus I infinity, which is 10 ampere, e to the power minus t over tau. Tau is 5 in this case. And finally, we get the current equation for an inductor, which is 10 multiplied by 1 minus e to the power minus t over 5. Now let's summarize the important equations that we have learned so far in this lecture. Those are for transient and steady state response of RL circuits. The current equation is ILT equal IL infinity plus IL0 minus IL infinity e to the power minus t over tau. And the equation for voltage would be VLT equal VL infinity plus VL0 minus VL infinity e to the power minus t over tau. And finally, the time constant of the RL circuits will be tau equal L over R. Now you are ready to solve the practice question. Let's go and do that.